Okay, finally part 4. I'm going to get done with it in part 4. I'm going to just rush through this and get done with this in part 4. So an incomplete review of Unit D part 4. All right, so here we have a crate that's going to fly down a kind of a swooping inclined plane, and there's friction on this inclined plane, so it's gonna go down and it's gonna come to a halt. It will actually be zero speed here. It's gonna be zero speed. And so, could you tell me what the work will be? What work will be done by the normal force? How much work will the normal force do? Go ahead and pause. Okay, the normal force will do zero work because the normal force is perpendicular to the displacement at each point along the way. So that's zero. You tell me how much work the force of gravity will do. Go ahead and pause. Okay, the force of gravity is going to actually do some work. And so it's going to be the force of gravity times the displacement. Now, you only want to take the part of the displacement that's in this part of the displacement that's in the direction of the force. So it's going to be Fg times how much of this displacement is in the direction of the force, h of it. So it's going to be mgh. So the work done by gravity is going to be a positive mgh because the force is down and so is the displacement in the direction of the force of gravity. How about the work done by the net force? Go ahead and pause and tell me what the work done by the net force will be. Okay, we're back. The work done by the net force is always equal to the change in kinetic energy. And there was no change in kinetic energy. It started at rest and it ended at rest. And so the work done by the net force is zero joules. Okay, moving right along. Let's talk units for a little bit. You know what Newton meters is? What unit is Newton meters? Go ahead and pause. Okay, it's a joule. Can you tell me what unit joules per second is? Go ahead and pause. Okay, it's the watt. Can you tell me what Newton meters over seconds is? Pause. Yes, it's the watt. Okay, how about what's watts times seconds? What's watts times seconds? Pause. Okay, so a watt is a joule per second times a second, so that's a joule. Okay, could you tell me what kilowatts times hours, a kilowatt hour, what is that a unit for? What is kilowatt hours a unit for? Go ahead and pause. Okay, it's a unit for energy. This is energy. It's actually how the electric company bills us. It doesn't bill us for a certain amount of joules we use. It tells us how many kilowatt hours we use. That's the energy that if you were using power at a rate of 1 kilowatt hour, 1,000 watts for an hour, that's how much energy it is. So let's just do a quick calculation. 1 kilowatt is 1,000 watts, so that's 1,000 joules per second, and an hour is 3,600 seconds. So a kilowatt hour, if you want to know what a kilowatt hour is in terms of joules, it's 3.6 times 10 to the 6th joules. It's a lot of joules. All right, going on. If I ask you to tell me how much work this force does in moving from 0 to 2 meters, can you calculate that? Go ahead and pause and calculate that. Okay, we're back. Okay, so the way you got to do this, it's a varying force, so you have to put it into this. I'm not going to use the units. I'm just going to use, because I want to make sure I hit this deadline of 10 minutes here. I'm going to just put in 2x plus 6x squared dx. It's the force times dx, and then my boundary conditions are 0 and 2. All right, so I'm going to evaluate this. Go ahead and try and evaluate this on your own. Okay, so so this is going to be the antiderivative of just the integrand. And so that's going to be x squared plus maybe the x cubed 2. Let's see if that works. That would be me 2x, 6x squared. Yeah, that works. And then I'm going to go from 0 to 2. Okay, let me first put in 2. So when I put in 2 first, I get 4 plus 8, 16. Minus, now I'll put in 0 for each of these. So it's going to be 0 plus 0. And so the total work done is 20 joules. If you have a little more time, you might see how the units work out. The units will work out, and you probably should know how to do that. Okay, we're down to our last two. Okay, that we might be able to do this. Okay, so this is a pendulum. It's swinging down. It's got a length L and a mass M, and it's released from rest right here, and that's horizontal to the ground. And we want to know how fast will it be going when it reaches the 45-degree mark. Okay, go ahead and pause and try and figure that out. You're going to have an M and an L in your answer. Go ahead and pause. Okay, so the way you find this is E equals E prime. Okay, if you didn't try that, you might try doing that. You can pause at any point where you think you can complete it and see if you can complete it. Okay, so at first, I'm going to call this the potential energy equals 0 line. You can call any line you want the potential energy equals 0 line, any horizontal line you want. Okay, so that means that this has some potential energy. How much potential energy? This height, which is, if this is L, then this side is L over the square root of 2. You can use some trig to get that. This is going to be 45 degrees. And you can figure out what that is. That's going to be L over the square root of 2 then. That's the height. So I'm going to use MGH. That's what it starts out with, mg, and h is L over the square root of 2. That will equal, when it gets to this spot, it doesn't have any potential energy, but it does have kinetics, so 1/2 mv squared. So we can cancel out m's. And solving for v, maybe I'll multiply both sides by 2. 2gl over the square root of 2 is equal to v squared. So v is equal to this. Got a radical underneath a radical, and the radical is in the denominator, but you get the idea. Okay, and lastly, okay, we're going to drop this ball. Now there is air resistance, so there's going to be air resistance, and so we're just throwing that in here. It starts out with no velocity. It's got a mass of 2 kilograms. It reaches the ground at 6 meters per second. Can you tell me what the work done by the force of air resistance is? What is the work done by the force of air resistance? Okay, go ahead and pause. Okay, the way you do this is you can use the generalized work energy theorem. U plus K plus the work done by the non-conservative force is equal to U prime plus K prime. Okay, so at first up here we have only U, so that's going to be MGH, so M times G, so 20 times, so it's going to be M times 20, it's 20 times, okay, so it's going to be 80 joules. But it doesn't have any kinetic energy up there. Plus the work done by the non-conservative force, which is what we're after, is equal to U prime, there's no energy there, plus K prime. Now K prime is 1/2 M, so those are going to cancel out. So it's 36 joules. So how much energy is done by the non-conservative force? 44 joules. Okay, then they might ask, how much work is done by the net force? So go ahead and pause and try and find the work done by the net force. Okay, we're back. The work done by the net force is the change in kinetic energy. It always is. And so it changed its kinetic energy. It went from 0 kinetic energy to 36 joules of kinetic energy. So that's how much work was done by the net force, 36 joules. All right, thanks.